Hello and welcome to this clip looking at a buffer pH exam question. So it starts off by giving us details of the acid being used, the weak acid, glycolic acid, and it's got a pKa value of 3.83. It's a weak monobasic acid, so that means it dissociates to release one hydrogen ion. It also tells you a little bit about a buffer solution that's being prepared, giving you details of the volume and the concentration of the glycolic acid and the strong base it's added to, the potassium hydroxide. So the first thing to do is to work out the moles of each of those two components. And as you can see, the number of moles of glycolic acid exceeds the number of moles of potassium hydroxide, so we get what's called a partial neutralization. So that means that there's some glycolic acid left behind and also some new conjugate base, or potassium glycolate salt. Those two things together allow a buffer solution to form. So the next thing to do is to calculate the pH of the buffer solution that is formed by putting in the moles we've worked out. Now for the glycolic acid, the starting moles is 4.5 times 10 to the minus 2. I'm using the ICE method, obviously the initial moles, the change in moles, and the equilibrium moles. Now we started out with 2.5 times 10 to the minus 2 moles of KOH. So what's going to happen is that will neutralize an equal quantity of glycolic acid, in the process getting used up. So we subtract that amount from itself to give us 0. So it'll make an equal quantity of conjugate base, or potassium glycolate salt, that wasn't there before. So we put in 0 to start with, we add on 2.5 times 10 to the minus 2, which gives us that amount at equilibrium. Now by partially neutralizing the glycolic acid, some of the glycolic acid will be used up. The amount will be the amount of strong base was added. So you subtract 2.5 times 10 to the minus 2 from your original 4.5 times 10 to the minus 2, which gives us 2.0 times 10 to the minus 2. So now we have to convert those moles into concentrations. To do that, you take the equilibrium moles and divide that by the total volume. The total volume can be worked out from adding the two quantities together, which is 100, obviously, in this case. So to calculate the pH of the buffer solution, you've got to work out the concentration of H+ ions at equilibrium. So once those two things have been added together. So to do that, you start with the Ka expression, and we start populating that Ka expression with the numbers that we can work out, or the numbers that we have. So to get the Ka from the pKa, you do 10 to the minus pKa, in this case 10 to the minus 3.83, which gives us that 1.479108388 times 10 to the minus 4. So to get the concentration of potassium glycolate, or the glycolate ion to be precise, you take its quantity at equilibrium, the 2.5 times 10 to the minus 2, and you divide it by the total volume, which is the 100 centimeters cubed over 1,000 to get it into decimeters cubed. You do the same to your glycolic acid, and that now allows us to isolate the hydrogen ion concentration. So we rearrange the equations so to make the H+ concentration the subject. You put in the numbers, and that gives you 1.1832871 times 10 to the minus 4. That then goes into the pH calculation, which is minus log of that quantity, and that gives us 3.93, remembering that you always put pHs to 2 decimal places. So let's now have a quick look at the marking to see how we did. So you can see that they put that up there for 4 marks. And if you have a look through, you start off with the initial moles. You work through what happens during the reaction to calculate the moles in the buffer solution. You get the pH by making the hydrogen ion concentration the subject, and that gives you 3.93. Okay, thanks for listening. Until next time, see you soon.